Genus, huh?
So my project was on a plant called Ulei, and it's really quite common here in Hawaii. It's awesome. And what got me interested in my project was, I traveled a lot in South America, and talked to Shawn and stuff like that, who work with medicinal plants, and it got me wondering what was in the plants they were showing me. So when we came out to school here, I tried to see if there's a plant I could study, see what's inside, see what explains its biological activity. So after a lot of looking, I couldn't find anything until AJ Patton's like, "Hey, Shawn, I'm leaving. Take my plant." Very nice. So here's my presentation. Hawaiian traditional medicine. Discovery of triterpenes in most humilities and related polio using T-cells. So with the native Hawaiian medicine, so back in pre-European contact Hawaii, you would have medical priests called kahuna la'au lapa'aus, who would use la'au, which is herb in Hawaiian, as medicine, because that's what they had. And they would, they would live by trial and error. And based on what they knew, they would pass that knowledge and information on to the next generation. And as you can imagine, that's a very important role back then as it is today. So the plant is called Ulei in Hawaii. And you'll find it like kind of by the coast, like a lot of dry spots, or kind of semi-wet areas. If you drive down towards Kaneohe, and you see the hills, the part close to the road is covered with this plant. And it's also found in the Rafa Islands in French Polynesia, Pitcairn. There's one plant left there. The Rurakomba, the Island, Tonga. So it's found, it has a pretty wide range over the Pacific, which makes sense as, birds would eat seeds and take those places. So the plant has kind of it has these white berries. They have very bitter taste to them. They are edible. And it has a few white flowers. The Kahuna Hawaiian priest, they had a couple uses for this. The one I was most interested in is they would take the bark from the root and they grind that up with the leaf with salt water, kind of make a paste, and then you bind that to wounds, which would help it heal. Question is why? Also, you could take the young leaves and the seeds from the berries, and you could chew on them and eat them, which would treat Aya and Pa'au. So what is Pa'au? It is, this is the word for childhood weakness. And Aya, my favorite, is thrush. Thrush is a fungal mouth infection. And I have kindly provided two pictures of that. So, very, very nice. So, the experiment is actually pretty simple. You collect the plant. I separated the leaves, got the root bark. The root bark is actually really hard to get, but sharp knife helped out. And the berries, which freeze in a little bit of nitrogen. Make sure I extract as much as I could. I left them overnight in chloroform, mix them up, and then I would pass them through a 2-micron filter so they could pass through GCMS. So for those who aren't familiar with GCMS, the first part, the gas column, will separate your compounds in your extraction based off hydrophobicity. So the more hydrophobic they are, the slower they will pass through your PCS. And they will come out the end at different times. This is your stationary and your mobile phase. You can see how different molecules move at different rates. Once they're eluted from the end of the column, they go into what we call the mass spectrometer. Basically what it will do is it will ionize and break up the molecules that pass through it, and then based off their size, a magnet will bend them and it'll hit a detector. And what it'll do is you'll get a characteristic mass spectra. So every molecule that comes through, it's like a fingerprint. And you'll have the molecular fingerprint or mass spectra for that compound. Here we have fuel and alpha-amine. And then a computer can read the mass spectra of your extraction, and then it can compare that against a library and give you a pretty good idea of what is in your extraction solution. This is pretty cool, by the way. We have to do that. So the computer will take an integral where we'll quantify the amount of material that passes through the mass spectra at a given time. So as you can see here, at 8 minutes, a whole lot of material came through. 13 minutes, not very much. And then you can click on it. You can, on the computer program, you're able to look at any of these peaks and see what fragments were passed through. So these peaks right here are long alkyl chains. So understandably, there's pull-up. It's part of the structure. This is probably stereol, there's a lot of that. But after going through all the peaks, this right here was very, very interesting. Pulling that peak up, it showed that it likely has alpha-amine luteal and fatal, according to the computer's program. So, I got super excited because, having talked to Aaron Sanders, he found alpha-amine in his plant, and it had 3 cool properties for fuel system. I was sad. The next step to see if the chemical is in your solution is to do what's called peak enhancement. Pretty simple, just add the chemical to the solution. I added alpha-amine because that's what I had, and then I overlaid the 2 mass spectra, and what I did. All the peaks stayed the same, except for my tritryptophan peak. Alpha-amine luteal, it was enhanced. Providing strong evidence that chemical is in there. So, what's the biological activity of these tritryptophans? You have betalain, which has studies are showing that it has some anti-cancer potential. Pretty awesome. Alpha-amine luteal on the hand, super exciting. Alpha-amine has been shown to have anti-inflammatory properties. Luteal has been shown not only to have anti-inflammatory, but anti-protozoal and antimicrobial properties. Big deal, because when you don't have antibiotics, back in 1722, why? That can prevent gangrene. You can see gangrene going on. Oh, and as you see here are the tritryptophans. They have pretty similar hydrophobicity to the structure. which poses a problem. All three of those compounds having very similar hydrophobicity would be eluted from the column at the same time. So, do we have 1, 2, or all 3 of those triterpenes in the species? That's the question to be addressed. So I went through my leaf, my berry, and my root bark extract, and I saw this. This is from the root, which, if you remember, is what they would use to bind wounds. And this is the triterpene seed. Relative to everything else, there is a lot of it. So I got thinking, why did they use the root? Because there's a lot of it. High concentration. This is the green's the root. This is our berry, the black bavaria extract in this one, and the black is the remaining. And as you can see here, there's a lot of it in the root and not a lot in the other 2 parts of the plant. I just think it's so cool that we're seeing why the Hawaiians did what they did. So what more can be done? There's still a bit of work that can be done. We could separate the different parts of our plant extract through column chromatography. So take different fractions, hopefully isolate the triterpenes, and send that sample through the GCMS to see if we can get a better separation of the mass spectra, and therefore read if the fluid flow out and beta group. Because there's a lot of noise from other chemicals. And then we can also, now that the LCMS stuff is working well, determine the protein content of our plant. I would like to thank, if it happened, Dr. Scott, Dr. Kugler, and Aaron Sanders for answering questions I had and helping me along. And then, of course, doing Hawaii for providing a $23,000 machine and 20 raw materials. And the pictures are from people I'm hiking with. That's where those came from. Here are references. Any questions? I'm open for it.
All right.